Here's what we know about the periodic table. We know that the periodic table was originally built by this guy, Dmitry Mendeleev. Now, Mendelev's table didn't look like what we have now. It looked a little bit different, but he built it based on trends that were known at the time, trends in reactivities, patterns, and things like that. So it really shouldn't surprise us that there's other trends, other patterns that the periodic table can help us to describe, but also help us to understand. One we're going to start with is atomic radius. Atomic radius is going to be determined by a couple of forces. There's a push force, the electrons pushing away, repelling other electrons, and there's a pull force, a positive nucleus attracting the negative electrons. And not just the nucleus, but we're going to have to talk about something called effective nuclear charge. We'll come back to that in a couple of minutes. We also want to make sure we understand what's going on with the electrons. So when we talk about electrons, we're talking about valence electrons, and they're out here in the valence orbit. And we have core electrons, and they're in the core orbits. And for the radius is the distance between the nucleus and the valence orbit. So this distance here, which is a pretty messy way of drawing it, but we're going to live with it. Shielding is part of that combination of forces, and shielding is by definition the inner electrons, those core electrons, absorbing or soaking up or canceling out, however we want to think about it. They decrease the attractive force of the nucleus. So however you want to think about that happening, that's what's going on. Those core electrons reduce the effectiveness of the nucleus. So if I take, for example, an atom that has 3 orbits. Now, my third orbit here, my valence orbit, doesn't have any electrons in it yet, but they're coming. The 10 electrons that I have as my core electrons, those are going to stay the same as I start adding electrons. So let's start with sodium. Add 1 electron. So that 1 electron is shielded from the nucleus by 10 core electrons. And if I go across the periodic table to the end of the row where I've got chlorine, chlorine has the same 10 core electrons shielding it, but now it has 7 valence electrons that are going to be shielded. So you notice the shielding has stayed the same at 10, but I've gone from 1 to 7. You have a picture like this in your textbook, and it shows the radii of both the atoms and the ions. Now across the top of every row is the atom, and then below that is the ion. And you'll notice as you go left to right across the table, here's my atoms, here's my ions. We've got a couple of interesting patterns happening. We're going to focus our attention on just the atomic radius for a moment. So we're going to simplify the picture down, and you'll notice here all I've got is one kind of circle. Left to right across the periodic table, it looks like my circles are getting a little bit smaller. Top to bottom, my circles are getting larger. So let's look at each one of those patterns in turn. We'll start with top to bottom. I saw on that previous picture that the radius was getting bigger. My atoms got larger. Now, if I think about the Bohr atom, that just simply makes sense because I have a new energy level. That's the simplest, most accessible explanation for this. Top to bottom, new energy level. That new energy level is full of higher energy electrons. Those electrons are then further away from the nucleus. But I also have going on more shielding. So I now have even more core electrons shielding the outer electrons, the valence electrons, from the pull of that nucleus. Left to right, the story is a little bit different. The radius got smaller, but as I go left to right, I have an increasing nuclear charge. So as I go from, let's say, sodium with 11 protons to magnesium, 12 protons, to aluminum, 13 protons. So I'm increasing the nuclear charge all the time. I'm also increasing the effective nuclear charge because the amount of shielding was constant. So sodium has 10 shielding electrons, magnesium 10 shielding electrons, aluminum 10 shielding electrons, stays the same. So as I increase the number of protons and I have equal shielding, that's going to be staying the same. I also am putting electrons into the same orbit. So the new electrons that are going in as I move to the right, they're not going farther away, they're going into the same orbit. So now they're right beside each other. And that increases the amount of nucleus to electron attraction, more pull. So my push force, shielding, is staying the same, and my pull force, nucleus to electron attraction is increasing, so I'm going to have a smaller radius. As a graph, it looks something like this. Now you notice it doesn't always apply. A couple of spots where the pattern doesn't fit, and that's okay. We're not going to worry about that. We want to know the trend. What we notice is from here. So this one spot would be lithium, sodium, potassium, top to bottom. Radius is getting larger, left to right. So I'm working my way across a row. Our radius is getting smaller. Important part of the trend. Back to this large graph, and now looking at the bottom of each row. So here, and then of course here. Now, quick glance across that, I notice a couple of things. Number one, the pattern doesn't really seem to follow, but let's zoom in on just the left-hand side of the periodic table. If I look at just the left-hand side of the periodic table, I'm dealing with the metals. And if I look at their ions, I'm dealing with the cations all the time. Now, cations are positively charged ions. So in each case, I've been losing an electron. And now I have the same number of protons attracting fewer electrons. Not only that, more importantly, in the case of lithium, I've gone from having, say, 2 energy levels to 1. In the case of sodium, I've lost my valence orbit altogether. I've gone from having 3 orbits to 2. So I've lost a whole energy level. But also, I have the same number of protons attracting fewer electrons. So in other words, I have a greater attractive force for each electron. More importantly for us is the trend itself, that the positive ion is always smaller. And if I look at, say, a positive 1 ion here at sodium and a positive 2 ion with magnesium, I notice that the more positive it is, the smaller it is. And that comes back to this piece, greater attractive force per electron. Looking at the other side of that table, where I now have the negative ions. The negative ions are the anions. In each case, I am gaining an electron. And when I gain an electron, I've got the same number of protons. They're trying to attract more electrons, so they're kind of spread out a little bit more, or their attractive force is spread out a little bit more. And that weakens the amount of attractive force per electron. You'll also notice that if I look at a negative 1 ion to a negative 2 ion to a negative 3 ion, the more negative it is, the more extra electrons that I've added, the larger it is, because I have a weaker attractive force per electron. So if it's just 1 added electron, it's a little bit weaker. If it's 2 added electron, it's that much more weaker. The important part of the trend is here, larger than neutral. And the more negative it is, the more larger it is. Ionization energy, another important trend. Ionization energy by definition is the energy required to always remove an electron. So it makes it positive. And in order to do that, in order to remove the electron, I have to overcome the attractive force of the nucleus. Now think about this. Certain atoms have a greater pull on the electrons. They've pulled them in nice and tight. They've made it a nice small atom. And that means they're already holding on to those electrons more tightly. That means it's going to be harder to remove it. So atoms with a smaller radius have a higher ionization energy. Conversely, atoms with a larger radius, they're not pulling their electrons very tightly, so they are more able or more easily able to lose that electron. So you'll notice what we did. We spent a lot of time talking about why the atom is the size that it is, and now we're using that as our reason for the trend of ionization energy. If you were to look at a similar graph, you'd see this. Now again, there's a couple spots where the trend doesn't really work, and that's okay. But here I've got, down here, I've got my lithium, sodium, doesn't want to work, my sodium, and my potassium. And you'll notice that as I move my way down the table, down a column, it's getting easier to remove, and as I go left to right across, it's getting harder to remove. Top to bottom, ionization energy decreases and it increases. Now we've already talked about why, but expect to see the question why. Expect for me to ask you on a test, on an assignment, to explain why that happens. Now a couple of other questions I might ask you. Number one is, why does potassium always become +1 in compounds? It doesn't become +2. it becomes +1. Why wouldn't it do something different? And why do nonmetals not become cations? Ionization energy is the atom losing an electron. So I could take an electron away from anything, including a nonmetal, but that generally doesn't happen. Why not? You can think about that and you can be able to answer that in terms of ionization energy. If you were to compare radius and ionization energy, to see that generally speaking, as one goes up, the other one goes down. Too easy. Electronegativity, another one, another trend. The third one we're going to look at, and this is where we're going to stop it. Electronegativity, by definition, is the tendency. It's kind of a fluffy thing. It's not something that we have necessarily measured. It's almost like a number that we have assigned to each atom. And we've assigned it based on good data, but it's not something that can be easily measured. The tendency of an atom to attract an electron. So you put two atoms into a cage match with an electron, who wins? Who ends up with the electron? That's electronegativity. Whether or not an atom can do that attracting, pull an electron to itself, depends on two things. Nuclear charge. It's the positive charge that's going to attract that negative electron. And the atomic radius. How close can that electron get to the positive nucleus? Right? How far away is that absorbing charge, or is that attracting charge? The trend, very simply, from top to bottom, electronegativity decreases. And left to right, electronegativity increases. Think about this in terms of atomic radius. So top to bottom, my atom is getting bigger, its ability to attract an electron is getting smaller. See if you can think about the reason why that might be. Left to right, my atoms are getting smaller, the ability for an atom to attract an electron increases. Those are the three trends that we're going to look at. We're going to use them extensively in class. There's going to be questions where you have to explain these things. Even just here, I didn't really say a whole lot about why the trend is what the trend is. I want you to think about that and be able to take care of that on your own in class. We'll talk about it, but we're going to be expecting you to quickly make use of it. As a graph, electronegativity, not that interesting. As a by the way though, electronegativity numbers range from 0 to 4, where 4 is the highest. And fluorine has the highest electronegativity of any element. We're going to use electronegativity fairly extensively when we talk about bonding. We're going to use ionization energy for a few things. Radius, though, really becomes our reason for electronegativity and our reason for ionization energy. So, be ready for class. We'll take it up. We'll talk about it. We'll move forward. Thanks for watching.